Morning everyone. This week's special request for going over a topic is the difference between interference caused by division of wavefront and interference caused by division of amplitude, and also what is all that Fourier stuff about. So here we go. First off, interference caused by division of wavefront. Here we have four wavefronts travelling left to right, encountering a barrier with two gaps in it, so you should be recognising Young's double slits experiment. And the wavefronts pass through the two gaps in the barrier rather, and start producing curved semicircular wavefronts, which then interfere with each other and produce a series of maxima over here. So why is this division of wavefront? It's because the wavefronts are being divided up by having to pass through the barriers. So the wavefront is divided, interference patterns produced, and there we go. So you learned all about interference by division of wavefront many moons ago, and this year we've added to that with interference caused by division of amplitude. So how does that work? We have got an incident ray of light coming to the boundary between air and glass, refractive index of the air 1.0, refractive index of the glass 1.4. As we know, or should know, at that boundary, some of the light will be reflected and some of it will be transmitted or refracted. So we have a refracted ray and a reflected ray. The refracted ray travels through the glass, comes to the boundary between the glass and the air on the other side of our pane of glass, and again, some is reflected at the boundary and some refracts through the boundary. This ray that refracts through the boundary we're not really interested in for the purposes of division of amplitude and the interference pattern subsequently caused. So a reflected ray comes up here and lo and behold hits the boundary between the glass and the air. So yet again we have some light reflected. We're not really interested in that. It will eventually come over here, reflect again, yada yada, but that's a fibre optic cable and we're not really talking about that just now. Up here, some of the light will be transmitted through the boundary, refracted through the boundary, and we get interference between this ray of light and this ray of light. So any light waves that are reflected here, any light waves that are refracted through here, if they come together up here somewhere, they can cause an interference pattern. Now the important points are where the phase changes happen, because here we're going from optically less dense to optically denser. So we're going to have a phase change of pi. This reflected ray of light, its phase will be pi radians out of phase with that incident ray of light. This ray of light that's transmitted or refracted in and through the glass, no phase change here, because we're going from optically more dense to optically less dense. So there is no phase change there, and here again we're going from optically more dense to optically less dense. So again, no phase change here, which means that this ray of light, which has had its phase changed by pi radians, and this ray of light, which has not had its phase changed compared to the original instant ray of light, these two rays are now pi radians out of phase with each other, and that is equivalent to half a wavelength out of phase, and that means we get destructive interference. So here I've noted down what happens. We've got reflected rays of light out of phase by pi, hence destructive interference when 2dn cos theta equals m lambda. Now where on earth is 2dn cos theta come from? It's come from up here. Let's pull this back down a bit. 2, because the ray of light's going through the glass twice. Remember from when we first looked at this topic, the angles here are all massively exaggerated. This original incident ray of light is coming down almost vertically, but we have exaggerated the angles ridiculously to try and make it clearer what's happening. So 2D is twice the thickness of the glass, n is the refractive index of the glass, so our 2dn is simply the optical path that this light has travelled through the glass. In other words, how much further this ray of light has travelled in comparison to this ray of light. Cos theta, well, it is at an angle, and there's the angle theta in there between the normal and the refracted ray of light, and m lambda because it's destructive interference. But wait, you say, wait, we've been taught all along that m lambda or n lambda was constructive interference. Well, as I said when we first looked at this topic, yes, that's true. Unless, of course, some sneaky so-and-so has put in a phase change here, but no phase change here or here. So that means that what once was constructive, because of that phase change, is now destructive. And there we've got the constructive interference formula for this arrangement. 2dn cos theta, so the optical path difference, once again, equal to m plus a half lambda. And again, same explanation. Previously, we've always been taught something plus a half a wavelength means it must be destructive interference, but that's because there's a phase change there. So remember, you don't need to worry about phase changes for division of wavefront. Phase changes are absolutely critical for division by amplitude. Now, to make sure you're thinking about that, here's a little example for you to go and think about. What happens if this is the arrangement? A glass panel with a layer of oil on top of that and the air on top of that. And a ray of light is going to come in, let's try that again, is going to come in like so, and some of it's going to be refracted through, some of it's going to be reflected, some of it's going to be reflected, some of it's going to be refracted through. Are we going to get from these reflected rays here? There we go. Better remember to put my normal lines in. These rays, are we going to get constructive interference or destructive interference? And why? So the third thing that people were asking for a quick word on for this weekend was Fourier and waves. And what's that all about then? Well, essentially your man Fourier said, I can do, depending on whether I want to go from beginning to end or end to beginning, I can take lots of simple waves. So there's one simple wave pattern there. It's a sine wave. There's another simple sine wave there. And your man Fourier said, well, I can combine these two wave patterns, both mathematically and in the real world of physics, as opposed to the fantasy world of maths. And what that'll give me is a complicated pattern. So mathematically, I can take this sine wave, I can add it to that sine wave, and the result is this sine wave. So two simple ones make a complicated one. And of course, the more simple ones that you combine, the more and more complicated your final version becomes. Fourier obviously also turned that on his head and said, well, that means that I can take complicated wave patterns, and by expressing them, instead of one really horrible, nasty, complicated function, I can simply express them as the sum of various simple functions. So basically, no matter how complicated the waveform is, Fourier said, that's okay. Doesn't really matter how complicated it is, because I can either build it up or break it down using a sum of many, many, many simple waves. And that was really all that Fourier said, at least as far as advanced higher physics is concerned. Some of you may or may not be familiar with the name of Moog. Some of you may or may not be familiar with the name of Midge-Dure. Some of you may or may not be familiar with the name Ultravox. Moog was a professor of physics and electrical engineering, if I remember rightly, and he took Fourier's idea of analysing complex waveforms and how the complex waveforms, like music for example, was just built up from simple waveforms. And he applied that to electronics and produced the world's first electronic synthesizer and put it into production and made his fortune. Midgear and Ultravox were one of the first bands to take the electronic synthesizer and bring it into popular mainstream music and have it so successful that it had to be recognised as a proper modern musical instrument in its own right. And just to reassure you that nobody's going to ask you to do any horrible calculations to do with adding sine waves together to represent more complicated sine waves, or taking complicated sine waves, could be cosines of course, and breaking them down into simpler sine waves. This is what the starting point of the calculations would be here. So you may or may not be faced with something along those lines in your maths or your mechanics exams, probably not in statistics, but you're not going to be faced with a calculation like that in your physics exam.